There's a plane capable of flying over 20,000 kilometers without landing, 22 hours straight in the air, non-stop. No refueling, no touching down anywhere on the planet. It takes off in Sydney and lands directly in London. For decades, that flight was technically impossible. Not for lack of will, not for lack of money, but because physics simply wouldn't allow it. No commercial aircraft had the capacity to carry enough fuel to cover that distance without refueling. But something changed. And what changed wasn't physics. It was engineering that learned to work around it. Today, you're going to understand exactly how an airplane can fly over 20,000 kilometers non-stop, what modifications make it possible, what technical problems engineering had to solve that no one tells you about, and why this flight isn't just a record, but the beginning of something that will forever change the way the world connects. But there's one detail that almost no one knows about how this works internally, and that detail completely changes the way you see what you're about to hear. To understand why this is so extraordinary, we must first understand the problem. Geographically, Australia is a giant island at the edge of the world. It's so far from Europe and the east coast of the United States that for decades it was impossible to get there without at least one stopover. Dubai, Singapore, Los Angeles. There was always a mandatory stopover. That's not a logistical inconvenience. It's a physical limitation imposed by something very simple. Fuel. A conventional airplane can only carry a certain amount of kerosene. When that kerosene runs out, the plane has to land. And for decades, no airplane in the world could carry enough to cover the distance between Australia and Europe in a single leg. That simple. That definitive. And to achieve this, Airbus had to find space for another 20,000 liters of fuel inside an airplane that was already practically full. In 2017, the Australian airline Qantas decided that this limit had to disappear. They launched an internal program called Project Sunrise. The name isn't random. During World War II, when Singapore fell, Qantas operated Catalina flying boats from Australia to Sri Lanka to maintain the connection to London. Those flights lasted 33 hours. Passengers saw the sun rise twice before reaching their destination. It was pure human endurance, transformed into an aviation operation. Qantas took that spirit and brought it to Airbus with a very specific requirement. I need an aircraft that can cover 17,000 kilometers non-stop. Sydney to London, Sydney to New York. Direct. Airbus responded with the A350-1000 ULR. Ultra-long range. But this is where the first problem arises. One that no one explains well. A conventional A350-1000 is already one of the longest range aircraft in the world. It can fly more than 15,000 kilometers non-stop. It's an extraordinary machine in its own right. So what exactly was missing to reach 17,000? The answer lies in one figure: 20,000 liters. That's roughly equivalent to the fuel many cars would consume in their entire lifetime. That's the amount of additional fuel the aircraft needed to close the gap. And to carry those extra 20,000 liters, Airbus did something that seems simple, but required months of engineering and a complete recertification of the aircraft. They added an additional rear fuel tank. They call it the RCT, short for Rear Center Tank. It's not an external tank attached to the fuselage. It's integrated directly into the aircraft's structure, as if it had always been there. Those extra 20,000 liters extend the range by almost 2,000 kilometers, and that's exactly what was missing. But here's something that almost no one considers. 20,000 liters of kerosene isn't just fuel. It's weight. It's additional structural pressure during takeoff. It's a completely different distribution system that has to function perfectly for 22 hours straight. And there is another, even more interesting problem. And here, a problem arose that no one expected. It wasn't in the engines. It wasn't in the wings. It was in the galleys. An 8-hour flight has its own technical demands. The galleys operate for 8 hours. The climate control systems maintain the temperature for 8 hours. The air filters renew the cabin oxygen for 8 hours. Now multiply all of that by almost 3. And suddenly problems begin to appear that a conventional flight never has to face. The galleys on a 22-hour flight cannot be the same as those on a conventional flight. It's not a problem of food capacity. It's a problem of the refrigeration systems. On an 8-hour flight, those systems work sufficiently. In 22 hours, the accumulated load pushes them to limits for which they were not designed. And this is where engineering does something unexpected. Airbus developed a completely new galley refrigeration system for this aircraft. Lighter and more efficient units, specifically designed for the demands of ultra-long-haul flights. The result isn't just greater operational efficiency. It's a weight saving of 300 kilograms. 300 kilograms that, over 22 hours of flight, have a real and measurable impact on total fuel consumption. In aviation, weight isn't a static number. It's a variable that multiplies with each hour of flight. Every kilogram you reduce at the beginning of the journey is fuel you don't need to burn at the end. And that fuel you don't burn is weight you don't have to carry. And that weight you don't carry is more range. It's a cycle that aeronautical engineering knows well. And every improvement, however small it may seem, triggers consequences that amplify with distance. The most surprising thing comes next. This new cooling system isn't limited to this aircraft. Airbus has confirmed that this technology will become standard for the entire A350 family. What was developed to solve a specific problem on a 22-hour flight will benefit hundreds of aircraft flying conventional routes for decades. That's how cutting-edge engineering works. It doesn't solve a problem, it raises the bar for what's possible for everyone. But there's something that completely changes your understanding of this aircraft once you discover it. The A350-1000 ULR isn't simply a plane with more fuel. It's proof that the last real limit of commercial aviation wasn't technological. It was economic. For decades, the problem wasn't that no one knew how to make a plane that could fly 20,000 kilometers. Engineers knew perfectly well what was needed. The problem was that making such a plane profitable seemed impossible. A 22-hour sea flight with fewer passengers than the aircraft could technically carry. A crew requiring rest breaks during the journey. Systems designed to withstand twice the usual stress. The operating cost per seat on such a flight was, on paper, a difficult argument to make. Qantas made it another way. The aircraft will have a capacity of 238 passengers in 4 classes, 6 first-class Eton suites, 52 business-class suites, 40 premium economy seats, and 140 economy seats with generous legroom. This isn't the configuration you'd use to maximize revenue on a 3-hour route. It's a configuration designed with the understanding that whoever boards this plane will be on board for almost an entire day. And that reveals something fundamental about the business Qantas is building. They're not selling a cheaper flight. They're selling time. The time you gain back by not having to arrive 3 hours early at a layover airport. By not wasting half a day waiting for a connection. By not arriving at your destination having slept in 3 different places along the way. For those traveling in business or first class, that time has a value far exceeding the price of the ticket. And therein lies the economic viability that for decades seemed unattainable. And then came the moment to see if all that theory worked. The A350-1000 ULR's maiden flight took place on June 2, 2026. It took off from Airbus's facilities in Toulouse, remained airborne for 3 hours and 43 minutes, and reached an altitude of just over 12,500 meters. During that time, the test crew verified the overall aerodynamic performance and, above all, tested the complete architecture of the new fuel system. How the upper CT, rebound fuel tank, operates under real-world conditions, how it interacts with the aircraft's other fuel tanks, and how the system manages weight distribution as fuel is consumed. That first flight marked the beginning of a test campaign of approximately 2 months. Once completed, the aircraft will be reconfigured to Qantas's commercial specifications and the final certification process will begin. The second A350-1000 ULR is already in advanced stages of assembly in Toulouse. It will be the first to be delivered to the airline, with a planned delivery date in April 2027. Operational integration will follow, and finally, the start of commercial flights for Project Sunrise. Qantas has 12 of these aircraft on order. Non-stop flights from Sydney to London. Non-stop flights from Sydney to New York. Routes that for decades were geographically impossible for commercial aviation are about to become routine. What makes all this fascinating isn't the number of kilometers. It's what that number represents. For decades, geography determined how the world connected. If you lived in Australia, the rest of the planet was always on the other side of a layover. A wait, an intermediate flight. Access to the entire world always required mandatory stopover that no one asked for. An extra fuel tank, a more efficient cooling system, and months of recertification have just changed that. Not with a quantum leap, not with revolutionary technology that no one could have imagined, but with patient, stubborn, and precise engineering, solving each problem that appeared after the previous one until none remained unsolved. That's what aviation does when it decides something has to exist. If the world of aviation has piqued your curiosity, I've included another video on screen for you to discover more.